Hi everyone, this is Mrs. G, and today we're going to start learning about curve sketching. Alright, I have a warm-up for you guys to try, so please pause the video and give it a try. Alright, go ahead and check your work here. So you can see I kind of took the information from the checklist and I turned it in. I did a little sign analysis for the first and second derivative just to show where it's increasing and decreasing and where it's concave down or concave up. And remember, when our second derivative is equal to 0, that's a point of inflection. So you can see here at negative 1, 3, I'm changing from concave down to concave up. And then here at 2, 4, I'm changing back to concave down. So we can make a little note, this is a point of inflection. So do your best to show that it is changing concavity there. And since our graph is changing from increasing to decreasing at negative 3, we have a maximum somewhere at x equals negative 3. The y value it can be anything because it's not specified, but the x value needs to be at negative 3. And then here we're changing from negative to positive, so we have a minimum at positive 1. And then here we're changing from positive to negative, so again we have a maximum somewhere on the line x equals 4. All right, so today we're going to start working on what's called curve sketching, which is essentially just graphing functions using calculus. So we're really going to tie together all the different things we've been talking about, as well as drawing on previous knowledge of, finding zeros and different intercepts and what different types of functions look like and how they act. So we're going to kind of follow this little checklist as we go through our problems. There's a lot of steps to these problems. First, it's always important for us to look at the domain of our function so we could see if there's any holes or asymptotes we need to look out for. We should determine any intercepts, both x and y intercepts. Intercepts. We do need to see if there are any asymptotes, and that would include vertical asymptotes, so any domain restrictions, and horizontal asymptotes, which would be end behavior. And then we should also, it is useful for us to do a quick symmetry test to see if we are working with either an even or odd function, because if we are, it can actually cut our work in half. We only need to graph the right half of our graph, and we either just reflect it over the y-axis, or we would reflect it 180 degrees about the origin. So these are our tests for even and odd functions, and again, it's really just to save us some time when we are graphing. And then, just to help us get an even more accurate graph, besides just our intercepts and our asymptotes, we're going to use our first derivative to determine when our graph is increasing and decreasing, and to help us find a relative max or min, so we can use that first derivative test. And then we're going to use our second derivative to determine the intervals of concavity, so where we're concave up and concave down. And we're also going to use it to determine our points of inflection, which is where our graph changes concavity. So the nice thing about curve sketching is because we are tying so many different things together, it really allows us to graph a more accurate graph than just plotting some points and connecting them, because when you do that, you can really miss out on some subtle features of your graph. So knowing your first and second derivative and what it can tell us can really help us make a more accurate graph. All right, so let's see if we can give this one a try together. So here we're going to graph f of x equals x plus sine of x on the interval negative 2 pi to 2 pi. So first we are going to want to determine the domain, just so we can look out for any domain restrictions. We know that the domain of a linear function is all real numbers. The domain of any sine or cosine function is all real numbers. So the domain of f of x will be all real numbers for the interval negative 2 pi to 2 pi. All right, so now we're going to just look at our at f of x. We're not looking at the derivative yet, and see if we can determine intercepts, asymptotes, and we'll do a quick symmetry test. All right, let's start by finding our y-intercept. So for our y-intercept, we do f of 0, replace x with 0, and we get 0 and plus the sign of 0 is 0. So we see that we actually have a y-intercept at 0, 0, which is also an x-intercept. And then if you're looking for other x-intercepts, we won't see any. So again, if you set your equation equal to 0 and you start solving, we're wondering when is negative x equal to the sign of x, and the only time that that's going to occur is at 0, 0. So this is going to be our only x-intercept. Now, we know that there are no vertical asymptotes because there are no domain restrictions, so we can make a little note here. No, I'm going to say VA for vertical asymptotes because there are no domain restrictions. But we can look for horizontal asymptotes, which are essentially end behavior. So for that, we are going to need to do a limit as x approaches infinity. So let's do the limit as x approaches positive infinity. And here we can just try some direct substitution. So this will approach positive infinity. And we know that sine oscillates between positive 1 and negative 1 infinitely. So we could just say plus or minus 1. But since we have infinity plus or minus 1, we know that this function is going to approach infinity. And then, so that means that there's no horizontal asymptote, at least on the left. Let's see what's happening on the right. And now we can see what's happening on the left as x approaches negative infinity. So x will approach negative infinity, and going to the left, your sine function will do the same thing. It will kind of bounce between positive and negative 1. Regardless, because of this linear portion, this as x approaches negative infinity, f of x will approach negative infinity. So since there are no actual value limits, we can deduce that there are also no horizontal asymptotes. So we check our limits at infinity to help us look for horizontal asymptotes. And then here we can do our quick little symmetry test. Again, if we know if something is even or odd, it can actually save us some time. So for a symmetry test, we plug in negative x, and we see what happens. So if I substitute negative x for this portion of my graph, it becomes opposite. And we know that sine is actually an odd function. So the sine of negative x is actually negative sine of x. If you plug in the negative version, you get the of x, you get the negative output. So if you look at what we get, our function ends up being completely opposite. Both parts of our function are opposite when we plug in the opposite x value. So that's telling us that f of negative x equals negative f of x, which is the definition of an odd function. So that means that all of our points will be reflected 180 degrees about the origin. So again, that could save us a little bit of time. If we know points on the right side of our graph, we can just reflect them down to the left side. All right, so now we're going to move on to all of our work with our first derivative. So we're going to use our first derivative to determine any intervals of increasing and decreasing and to help us find our relative extrema. So first we need to find our first derivative. So the derivative of x is just 1, derivative of sine is cosine. So we do want to find our critical points, which is when our derivative is equal to 0. So we'll set our equation equal to 0 and we will solve. And for this interval, from negative 2 pi to positive 2 pi, we know that cosine is equal to negative 1 when x is negative pi and positive pi. So we can use these critical numbers to help us do a little sign analysis for our first derivative. So I'm going to have my endpoints here. So these are our endpoints. And then here's negative pi and positive pi, our critical points, and then we can plug in different values to see the sign of our first derivative. All right, so if we pick strategically, like if you pick negative 3 pi over 2, the cosine of that is 0, so we're just left with 1, so that gives us a positive. Maybe if you plug in 0, we get 1 plus 1, so another positive, and we could do positive 3 pi over 2, and that gives us the same thing. Also, if you think about it, cosine will always give us a value between positive 1 and negative 1. So even when it's at its minimum, we're still adding 1. So the minimum value here is really 0. So it will actually never go below 0. So at these points, at negative pi and pi, it touches the x-axis, but then it's always going to turn around. So it's positive in all 3 intervals. All right, so now we're going to say, well, what does this tell us about our graph? This tells us that our graph is increasing between negative 2 pi and negative pi, and then from negative pi to pi, and then from pi to 2 pi. And we can also see that since our first derivative is never changing signs, it's never changing from positive to negative or vice versa, we can also state that there are no relative extrema, there's no relative mins or maxes. So that is what we are able to determine from our first derivative. So now we're going to move down to our last portion where we're going to work with our second derivative, which will tell us intervals of concavity and our points of inflection. So let's start with our second derivative. The cosine of 1 is 0, the derivative of 1 is 0. The derivative of cosine is negative sine. So we are going to, well, first let's determine that this function is never undefined. Because we know that points of inflection could occur when our function is undefined. It's also important to note up here that our first derivative, we can make a little note of it, is also never undefined, because that could tell us something about our graph as well. So our second derivative is never undefined. So let's see when our second derivative is equal to 0, because that will give us our points of inflection, and it will also allow us to do the intervals of concavity. So I'm going to set my equation equal to 0. We can divide both sides by negative 1. So within our interval, we know that, well, it is 0 at negative 2 pi, but we don't want to include negative 2 pi. And then it'd be 0 at negative pi, 0 pi. It is 0 at 2 pi again, but that's not part of our open interval, or so we aren't going to include it. So these are the 3 x values for our points of inflection. Before I actually find those points of inflection, let's do our quick sign analysis here. All right, so our endpoints again are negative 2 pi to 2 pi. Then we have negative pi, 0, and pi. And again, we're doing a sign analysis of this function. So we know that usually our sine function starts at 0 and then goes up, but we have that negative out front, so that means it's going to be negative here. And then we know that it will cross back over at pi, so then it'll be positive here. And it kind of follows that pattern of going above and below the x-axis. So we can see which regions our graph is concave up and where it's concave down. So we can describe those. Remember, it is concave up when your second derivative is positive. So from negative pi to 0 and from pi to 2 pi. And it is concave down when our second derivative is negative. So negative 2 pi to negative pi and 0 to pi. And then we know that our points of inflection will occur when your second derivative is 0 or undefined, so we can plug in these values to our original function. which remember was x plus sine of x. So here's our original function. Okay, so if you substitute, let's start with negative pi. The sine of negative pi is 0, so we're just left with negative pi. And if we do 0, sine of 0 is 0, so we're left with 0. And the sine of pi is 0, so we're just left with pi from the x. So our points of inflection would be negative pi, 0, 0, and pi, pi. All right, so now we have tons of information about our graph. So now we need to go sketch it. So the first thing I'm actually going to do is I'm going to define the scale of our graph. So you can see that everything is kind of in terms of pi. So I'm going to call this pi, and this is 2 pi, negative 2 pi, and I'll scale my y-axis by pi as well. So if we go way back up to our first part, we know that our x and y-intercept are at the origin, and again we have no asymptotes, so I'll plot that point. It will also be useful for us to, we'll need the endpoints of our graph, so we should also find f of 2 pi. So the sine of 2 pi is 0, plus 2 pi is 2 pi, so one of our endpoints is 2 pi, which would be up here. That's an endpoint. And then we'll find our other endpoint at negative 2 pi. So if you plug that in here, again, sine of negative 2 pi is 0, so that just leaves us with negative 2 pi, so that's our endpoint. On the left, so down here. Okay, other points that we should plot would be our points of inflection, because that's where we're going to be changing concavity. So we have negative pi, 0, 0 we already have, and pi, pi. So remember, this function is always increasing. So we know from left to right our graph is going to be going up. So really, the only way we can make our graph more accurate now is taking into consideration our concavity. So remember, if we didn't know about concavity, we might just go in and just connect the dots and we would think it's a straight line, but that's not a very accurate graph, because we know between negative 2 pi and negative pi from here to here, our graph is actually concave down. So it wouldn't just be a straight line, it would be kind of an arced line like this. Like that, to show it's concave down. And then in our next interval, here's our point of inflection. From negative pi to 0, we know that our graph is concave up, so it would go something like this. And then that's our next point of inflection, and then our graph is concave down. And then our graph is concave up. So again, this is a point of inflection. This is a point of inflection, and this is a point of inflection. All right, so we've used everything we know from our original function, from our first derivative, and from our second derivative. So we have a nice, accurate graph. So that means we're done with this problem. All right, let's try another one together. So we're going to go through the whole process again. Here our function is f of x equals e to the 2x minus e to the x. So first, looking at the domain of this function. Oh, and note that we're not graphing it over an interval, we're just graphing the entire thing. So the domain of e to the x is all real numbers, so this function has a domain of all real numbers. So we don't need to worry about any domain restrictions. So now let's work with our original function to find, we'll start with the intercepts. So we can start by plugging in x was 0, and that will tell us our y-intercept. So we get 1 minus 1, which is 0. So 0, 0 is one of our intercepts. And then we should also set y equal to 0 to see if we can find more intercepts. So here we have a GCF of e to the x, so e to the x minus 1. So from here, if you do zero product property, this will never equal 0. because if you're taking approximately 2.7 and raising it to a power, it will never be 0, it will never be negative, it will always be a positive number. And then here we can solve this using the zero product property. We want to know when is e to the x equal to 1, and that's when x is equal to 0, because anything to the power of 0 is 1. But we already have that coordinate up here. That's our x and y intercept. So that's our only intercept for this graph. Now for asymptotes, here we know, I'll make a little vertical line like this to separate it. We know that since there's no domain restrictions, we know that there's going to be no vertical asymptotes, again, because our domain is all real numbers. But we should look for our horizontal asymptotes, so we'll take the limits at as x approaches infinity. So we have e to the x times e to the x minus 1. So here we get infinity times infinity, which is infinity. And then if we do the limit as x approaches negative infinity, and notice I'm working with our factored function, so we don't have the infinity minus infinity, which is an indeterminate. Here, e to the negative infinity, that's 1 over e to the infinity, so this will actually approach 0. And here, this portion will approach 0, and then we have 0 minus 1, so 0 minus 1 equals 0. So in terms of horizontal asymptotes, as x approaches positive infinity, it's just going to increase without bound, but to the left, we actually do have that horizontal asymptote. So we have the horizontal asymptote at y equals 0, and again, we have to remember that that's as x approaches negative infinity, so only to the left. And then if we do a quick test for symmetry, we plug in negative x and we see what we get. So we get e to the negative 2x minus e to the negative x. So here they are, they're not the same, but they're not exactly opposite because we do have these negative exponents. So our result is, well, it's not equal to f of x, so that means it's not even, and it's not equal to negative f of x, so that means it's not odd, so it's neither even nor odd. So we can't use symmetry to help us at all for this problem. All right, so now we're going to move down to our first derivative work so we can find where it's increasing and decreasing and determine any relative extrema. So let's start by finding our first derivative, f prime of x. So if you do the derivative of e to the 2x, don't forget to do our chain rule here. It's 2e to the 2x, and the derivative of e to the x is just e to the x. So it is important to note that since we are looking for critical points, that this is never going to be undefined. So I'll make a little note here, never undefined. So now we need to check to see when our first derivative is equal to 0. So we can factor again. We can factor out e to the x. And again, this will never be equal to 0. So I'll make a little note, never 0. But then we can set this factor equal to 0. So we get e to the x equals 1/2. So rewriting this as a logarithmic expression gives us x equals the natural log of 1/2. So this is going to be our critical number. I'll make a little note. Okay, so we're going to do a little bit of sign analysis with our critical number. So here is the natural log of 1/2. And when we're doing this sign analysis, remember that e to the x is always going to be positive, this factor. So we're really just doing a sign analysis for this factor here. So the natural log of 1/2 is about negative 0.7. So if you plug in any value into this factor or your entire function, either way would be fine. Like if we plug in -1, we actually get a negative value. And then if you plug in anything larger, like 0, you would get a positive number. So it's positive here. So you can see that our derivative is changing from negative to positive at our critical point, which means that we will have a relative minimum there because we're changing from decreasing to increasing. So again, that gives us that minimum. So let's describe our intervals. So our graph is increasing here, so from the natural log of 1/2 to infinity, and it's decreasing from negative infinity to the natural log of 1/2. And we need to figure out what the coordinate of that minimum value is. So we do need to substitute natural log of 1/2 into our original function. So remember, our original function is e to the 2x minus e to the x. So we'll find f of natural log of 1/2. So we have e to the power of 2 natural log of 1/2 minus e to the natural log of 1/2. So as we simplify here, e to the natural log of 1/2, this part is 1/2, and then we're still going to square it. So we simplified this portion, we're still going to square that. And then here, e to the natural log of 1/2 is just 1/2. So we have 1/4 minus 1/2, which is negative 1/4. So our coordinate for our relative minimum is the natural log of 1/2, negative 1/4. So I'm going to highlight that coordinate here, and I'll highlight our intervals of increasing and decreasing. Okay, so we're done working with our first derivative. So now we need to move on to our second derivative, so we could determine points of inflection and concavity. So we'll take the derivative of our first derivative. So we get 4e to the 2x minus e to the x. So again, this function is never undefined. So I'll make a little note. Never undefined. So that means that our points of inflection would only occur when it's equal to 0. So we can factor out e to the x. And again, this is never equal to 0, and so we have e to the x. If I set this equal to 0, equals 1/4, so x equals the natural log of 1/4. So this is what we will use to help us do our sign analysis of our second derivative. So let's say we plug in some number less than the natural log of 1/4. So let's say we plug in like -2. This factor is always going to be positive. This factor would actually be negative. So our graph is, so our second derivative is negative here. And if you plug any value to the right, you will get a positive value. So that means that our graph is concave down when our second derivative is negative, so negative infinity to the natural log of 1/4, and our graph is concave up from natural log of 1/4 to positive infinity. And you can see that we are actually changing concavity, so we're going from concave down to concave up, so this is our point of inflection. So then we need to substitute that into our original function. So f of natural log of 1/4 equals e to the power of 2 times natural log of 1/4 minus e to the power of natural log of 1/4. So remember here, e to the power of natural log of 1/4 is just 1/4, but we still need to square it. Here, this is just 1/4. So we have 1/16 minus 1/4, so that gives us negative 3/16. So our point of inflection is natural log of 1/4, negative 3/16. All right, so now it's time to graph our function. So remember, our only intercept was at the origin. Maybe first I'm going to scale my axes, actually. So I'll scale here by 1. So here's -1 and -2. And I'll scale my y-axis in the same way. Here's -1. Okay, so our only intercept, again, was at the origin. We can plot our point of inflection and our relative minimum. So just to get an idea of where this is, the natural log of 1/4 is about -1.4. And again, natural log of 1/2 is approximately -0.7, just to help us plot those points. All right, so our relative min would be somewhere right around here. And then our point of inflection would be somewhere maybe right here. Just kind of have to do your best to estimate. And then we can also look at our concavity. So again, we're going to be concave down in this region here until we hit our point of inflection, which is right here, in which case we're going to be concave up from here on out. So remember, for our end behavior, as x approaches positive infinity, our graph is going to increase without bound, but on the left we do have that horizontal asymptote at 0, so then we'll use that to help us make the shape of our graph. So again, that horizontal asymptote is only for on the left. So, and here we are concave down. So our graph kind of does something like this, and then we change to concave up, and then we just kind of keep increasing without bound. So like this, something like that. And there you go. So it is a little bit tricky to kind of see. This is concave down, and then it changes here to concave up. And here is our relative min. And we are all set. So you can see that there's definitely a lot to these problems. So it's really important, that you keep your work organized. It's really important that you understand, okay, what does our first derivative tell us? What does our second derivative tell us? And then once you have all of your information, you have to be able to, piece it together with your graph. But that is all for today's video. So thank you guys for watching.